Hey, sleepers. Welcome to Sleepy Lectures, the show where bedtime meets the boundless cosmos, and staying awake is strictly optional. Tonight, we're journeying into a world that is both impossibly small and infinitely vast. A world that powers our sun, builds our reality, and yet seems to follow a set of rules dreamed up in a fantasy. Imagine a soft, deep blue mist. It hangs in the air around you, cool and quiet. Within this mist, tiny, shimmering lights begin to appear. They pulse gently, like distant fireflies on a warm summer evening. Some are gold, some are silver. They drift and dance, not in straight lines, but in gentle, unpredictable arcs. This is the realm we are about to enter, a place of potential and possibility. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as you settle in, perhaps you could share your location and your local time in the comments below. It's always so wonderful to think of this community of sleepers, spread all across our spinning world, listening together under different stars. So, close your eyes, take a deep breath, and get ready to drift off as we explore the fascinating science behind quantum physics and more. Let us begin our journey not in the strange world of the quantum, but in a place that feels much more familiar. A world of certainty, a world of solid, dependable rules. Let's drift back in time to the age of classical physics, the world of Sir Isaac Newton. Picture a grand old library. The air smells of aged paper and polished wood. Sunlight streams through a tall window, illuminating dust motes dancing in the air. On a large oak table sits a beautiful, intricate clock. Its gears turn with perfect precision. Each tick is followed by a talk. You can watch the second hand sweep around its face, and you know, with absolute certainty, where it will be in the next moment, the next minute, the next hour. This clock is a perfect metaphor for the classical universe. In this view of the world, everything was predictable. If you knew the position and the speed of an object, you could calculate its entire future and its entire past. Imagine a game of pool, a very, very simple game. If you know the exact angle of the cue stick, the exact force of the strike, and the exact position of all the balls on the table, you could predict the outcome of the break perfectly. You would know which balls would fall into which pockets, and in what order. The universe, according to classical physics, was just a much, much larger and more complicated pool table. The planets in the sky followed this beautiful clockwork motion. The tides rose and fell with predictable grace. An apple falling from a tree would always accelerate towards the ground at the same rate. This was a comforting world. It was a world of cause and effect. A world where things made sense in a very straightforward way. There was a satisfying solidity to it all. And in this world, we had two main categories of things: particles and waves. Particles were like tiny, solid marbles. They were distinct objects. They had a definite location. A baseball is a particle on a large scale. A grain of sand is a particle. You can hold it. You can point to it and say, "It is right here." Two particles cannot be in the same place at the same time. If you throw two baseballs at the same spot, they will collide and bounce off each other. Simple. Waves, on the other hand, were different. A wave wasn't a thing in one place. It was a disturbance, a vibration that traveled through a medium. Think of the surface of a still, quiet pond. It's perfectly flat and calm. Now, you gently touch your finger to the water. Ripples spread out in perfect circles. Those ripples are waves. They don't have one single location. They are spread out. And waves do something very special that particles do not. They interfere with each other. Let's stay by that peaceful pond for a moment. Imagine you touch the water in two different spots at the same time. Two sets of circular ripples spread out. As they travel, they meet. In some places, the peak of one wave meets the peak of another. They add together, creating a much higher peak. This is called constructive interference. In other places, the peak of one wave meets the trough, the low point of another. They cancel each other out, and the water becomes perfectly still in that spot. This is called destructive interference. The result is a beautiful, complex pattern of high crests and calm spots. An interference pattern. A scientist named Thomas Young demonstrated this with light in the early 1800s. He shined a beam of light at a screen with two thin, parallel slits in it. If light were made of tiny particles, like little marbles, you would expect to see two bright lines on the wall behind the slits, right where the marbles went through. But that's not what he saw. Instead, he saw a pattern of many bright and dark stripes, an interference pattern. This was clear proof that light behaved like a wave. The light waves were passing through both slits at once and interfering with each other, just like the ripples on the pond. So, the world was neatly divided. Matter was made of particles. Light was a wave. Energy was thought to be continuous, like a smooth ramp. You could have any amount of energy you wanted. You could be on any part of the ramp, from the very bottom to the very top, and everywhere in between. Everything had its place. Everything was understood. Or so we thought. As the 19th century came to a close, a few small, stubborn clouds began to appear on the clear blue sky of physics. They were small problems, little anomalies that didn't quite fit the perfect clockwork model. Most physicists thought they would be cleared up soon enough. But these weren't just any clouds. They were the harbingers of a storm, a revolution that would change our understanding of reality itself. One of these clouds was something called the black body radiation problem. It sounds complicated, but the idea is simple. Everything that has a temperature emits light. You, right now, are glowing. Your chair is glowing. The book on your nightstand is glowing. We can't see it because the light is in the infrared part of the spectrum, but it's there. A hot stove poker glows red. Heat it up even more, and it glows white hot. Scientists wanted to understand the relationship between an object's temperature and the colors or frequencies of light it emits. They imagined a perfect theoretical object called a black body, an object that absorbs all light that hits it and emits light perfectly based on its temperature. When they used the rules of classical physics, the elegant, trusted rules of Newton, to predict the light from this black body, they got a result that was completely, utterly wrong. The equations predicted that as you looked at higher and higher frequencies of light, like ultraviolet light, the object should emit more and more and more energy. In fact, it should emit an infinite amount of energy. This was a disaster. It was nicknamed the ultraviolet catastrophe. Think of it like this. Your radio can pick up radio waves. Your eyes can see visible light. An X-ray machine sees X-rays. Classical physics was saying that a simple, warm object should be blasting out lethal amounts of X-rays and gamma rays. But of course, they don't. A cup of warm tea doesn't give you a sunburn. So the theory, the beautiful clockwork theory, had to be broken. Something was deeply wrong with the fundamentals. This is where our story truly begins. In the quiet, desperate mind of a German physicist named Max Planck. Planck was a conservative physicist. He deeply respected the classical tradition. He didn't want to break physics. He just wanted to solve this one nagging problem. He spent years trying to fix the equations using the old rules, but nothing worked. Finally, in the year 1900, in what he later called an act of desperation, he tried something radical. He threw out a wild idea. What if energy wasn't a smooth, continuous ramp? What if it was more like a staircase? What if energy could only be emitted or absorbed in tiny, discrete packets, little chunks? You couldn't have just any amount of energy. You could only have one chunk, or two chunks, or three chunks, but never 1.5 chunks. He called these little packets of energy quanta, from the Latin word for how much. Imagine you're buying candy from an old-fashioned gumball machine. You can put in 1 coin and get 1 gumball. You can put in 2 coins and get 2 gumballs. But you can't put in half a coin and get half a gumball. The candy comes in discrete units. Planck was suggesting that energy itself behaved this way. When he plugged this strange, almost heretical idea into the equations for blackbody radiation, the ultraviolet catastrophe vanished. The math suddenly worked perfectly. It precisely matched the experimental results. Planck had solved the problem, but he was deeply unsettled by his own solution. He thought of it as a mathematical trick, a kludge that just happened to work. He didn't believe it reflected the true nature of reality. He had opened a door to a new world, but he was afraid to step through it. He hoped someone else would come along and find a more sensible, classical explanation. But the door was open. And a few years later, a young, brilliant, and famously irreverent patent clerk in Switzerland would not just step through that door, but kick it wide open. His name was Albert Einstein. In 1905, a year he later called his miracle year, Einstein published 4 groundbreaking papers. One of them took Planck's strange idea of quanta and applied it to a different problem, the photoelectric effect. The photoelectric effect is another simple-sounding phenomenon. When you shine light on a piece of metal, sometimes it can knock electrons loose. This is the basis for solar panels, in a way. The strange thing was, the ability of light to knock an electron loose didn't depend on the brightness of the light, but on its color. Using the classical wave theory of light, this made no sense at all. A brighter light is a more powerful wave with more energy. It should be better at knocking electrons out. A dim light is a weak wave. It shouldn't be able to do much. But experiments showed that a very bright red light, no matter how intense, might not dislodge a single electron, while even a very faint blue or ultraviolet light could start knocking them out immediately. Think of it like trying to knock a coconut out of a tree by throwing things at it. The classical wave theory is like trying to use a fire hose. A powerful fire hose with a lot of water, a bright light, should surely be able to knock the coconut down. But in the experiment, the powerful fire hose of red light did nothing. Meanwhile, a different approach, using faint blue light, worked. Einstein thought about Planck's quanta. He proposed that if energy comes in packets, then maybe light itself travels as little particles of energy. He called these particles photons. The energy of a single photon, he said, was determined by its color, or its frequency. Blue light has higher frequency than red light, so a photon of blue light is like a single, heavy, fast-moving marble. A photon of red light is like a lighter, slower marble. Now the photoelectric effect made perfect sense. It's not about the total power of the fire hose. It's about the punch of the individual projectiles. The bright red light is like being showered with a million tiny, lightweight ping-pong balls. They might be numerous, but no single ping-pong ball has enough energy to knock the coconut loose. The faint blue light, however, is like being hit by a few individual heavy baseballs. Even if there are only a few of them, each one has enough energy on its own to do the job. This was revolutionary. Thomas Young's experiment had proven that light was a wave. Einstein's explanation of the photoelectric effect proven that light was a particle. How could it be both? This was the first great paradox of the quantum world, the birth of wave-particle duality. Light, it seemed, had a split personality. Sometimes it behaved like a spread-out wave, as seen in the double-slit experiment. At other times, it behaved like a localized particle, a photon, as seen in the photoelectric effect. It's like having a creature that is both a cat and a dog at the same time. You can't quite picture it, but the evidence was undeniable. It depended on what question you asked it. If you set up an experiment to look for a wave, you found a wave. If you set up an experiment to look for a particle, you found a particle. Let this idea just settle in your mind for a moment. Don't try to force it to make sense. Just let the gentle contradiction exist. A wave and a particle, held together in one strange shimmering essence. It's like looking at a special kind of coin. One side shows a wave, the other side shows a particle. You can only see one side at a time, but it's always the same coin. The quantum revolution was now fully underway. The old clockwork universe was beginning to tick very, very strangely. And the next target for this revolution was the very heart of matter itself, the atom. At the time, the prevailing model of the atom was a bit like a tiny solar system. It was proposed by a scientist from New Zealand named Ernest Rutherford. He had discovered a dense, positively charged core at the center of the atom, which he called the nucleus. And he imagined that tiny, negatively charged electrons orbited this nucleus, like planets orbiting the sun. It was a beautiful, elegant picture, but it had a fatal flaw, according to the rules of classical physics. An orbiting electron is a moving charge, and classical physics was very clear that a moving charge should constantly radiate energy. As it radiated energy away, it would lose speed and spiral inwards, eventually crashing into the nucleus in a fraction of a second. If this were true, every atom in the universe would be unstable. The chair you're sitting on, the air you're breathing, you yourself, all would collapse in a flash of light. But clearly, they do not. The world is stable, matter is solid. So once again, the classical model was broken. The man who took the next great leap was a Danish physicist named Niels Bohr. Bohr was a brilliant, thoughtful man who worked with Rutherford. He looked at the planetary model of the atom, and he looked at Planck's and Einstein's new ideas about quanta, and he put them together in a daring way. Bohr proposed that the electrons in an atom weren't free to orbit at any distance they pleased. Instead, they were restricted to specific fixed energy levels, or shells. Think of it not as a solar system with infinite possible orbits, but as a special kind of ladder. The nucleus is at the bottom, and the rungs of the ladder represent the allowed energy levels. An electron can be on the first rung, or the second rung, or the third rung, but it can never, ever be in between the rungs. It exists in these specific states, and these states are stable. An electron in one of these allowed orbits does not radiate energy, and so it does not spiral into the nucleus. This was a bold new rule that simply broke with classical physics. And what happens when an electron moves from one rung to another? Bohr said it happens in an instant. An electron can absorb a photon of light with the exact right amount of energy, the exact right color, and jump from a lower rung to a higher rung. This is called a quantum leap. It's not a gradual climb. It's a disappearance from one rung and an instantaneous reappearance on another. Conversely, an electron on a higher rung can spontaneously jump down to a lower, empty rung. When it does, it emits a photon of light. The energy of that photon, its color, is precisely equal to the energy difference between the two rungs. Let's pause for a visualization moment. Close your eyes or just let your focus soften. Imagine a single glowing orb at the center of your mind. This is the nucleus of an atom. Around it, at various distances, are shimmering, translucent spheres. These are the allowed energy shells, the rungs on Bohr's ladder. Now, picture a tiny spark of light, an electron. It rests on one of the inner spheres, glowing contentedly. Suddenly, a pulse of golden light, a photon, comes from the outside and is absorbed by the spark. Instantly, the spark vanishes from the inner shell and reappears on a shell further out. It has made a quantum leap. It sits there for a moment in a higher state of energy. Then, just as suddenly, it drops back to its original inner shell. As it does, it releases its own pulse of golden light, which shoots off into the cosmos. This model was astonishingly successful. It perfectly explained the specific colors of light emitted by hydrogen gas. You see, when you heat up a gas, its atoms absorb energy, and the electrons jump to higher levels. When they fall back down, they emit light, but they don't emit a continuous rainbow. They emit a series of sharp, bright lines of specific colors. A barcode of light that is unique to each element. Bohr's model explained exactly why these specific lines existed. They were the signatures of electrons jumping between the specific rungs on the ladder for that particular type of atom. The world of physics was electric with these new ideas. Imagine the conferences of that time, the famous Solvay conferences in Brussels. Here, all the titans of this new science gathered in one room. A young, confident Albert Einstein, the revolutionary. The wise, fatherly Niels Bohr, the great synthesizer. The legendary Marie Curie, a pioneer of radioactivity and the only person to ever win Nobel Prizes in 2 different scientific fields. Her work on the atom's core was a critical piece of the puzzle, and her presence at these meetings lent immense gravity and insight. She was not just a chemist or physicist. She was a foundational thinker about the nature of matter. These minds would debate, argue, and challenge each other for days, trying to make sense of the bizarre new reality they had uncovered. The old world was gone, and they were drawing the maps for the new one. But the weirdness was only just beginning. Bohr's model was a brilliant stepping stone, but it was still a mixture of old and new ideas. It had orbits, a classical idea, but with new quantum rules tacked on. The next generation of physicists would push things into a realm of pure, unadulterated strangeness. In 1924, a young French prince named Louis de Broglie was writing his PhD thesis. He was a historian by training, but had become fascinated by physics. He had a simple, elegant, and profoundly strange thought. Einstein had shown that waves, like light, can behave like particles. De Broglie wondered, Could it work the other way around? Could particles, like electrons, behave like waves? He proposed that every moving particle, from an electron to a bowling ball to a planet, has a wave associated with it. A matter wave. The wavelength of this wave, he calculated, depends on the particle's momentum. For a large, heavy object like a bowling ball, the wavelength is so ridiculously tiny that it's completely undetectable. That's why we never see bowling balls acting like waves. But for a tiny, lightweight particle like an electron, the wavelength is much larger, large enough that its wave-like properties might actually be observable. It was a very bold idea, and his examiners were so unsure about it that they sent his thesis to Albert Einstein for his opinion. Einstein was intrigued. He saw the beautiful symmetry in the idea and encouraged them to accept it. De Broglie was awarded his Ph.D. A few years later, experiments confirmed his hypothesis. Scientists fired electrons at a crystal, and the electrons diffracted. They spread out and created an interference pattern, just like X-rays, which were known to be waves. The electron was a wave. Let that sink in. The electron, this tiny particle that we imagined as a little ball orbiting the nucleus, was also a spread-out wave of something. This discovery blew the doors off the atom once again. If the electron is a wave, then it doesn't orbit the nucleus at all. Instead, imagine a guitar string. When you pluck it, it vibrates. It can only vibrate in certain specific patterns or harmonics. It can vibrate as one whole wave, or in 2 sections, or 3. But it can't vibrate in 1.5 sections. The length of the string restricts it to specific standing wave patterns. The new picture of the atom, developed by physicists like Erwin Schrödinger and Werner Heisenberg, was that the electron waves were wrapped around the nucleus. The allowed energy levels, Bohr's rungs on the ladder, were simply the allowed standing wave patterns that could fit neatly around the nucleus. The electron wasn't a particle at a specific point in its orbit. It was a cloud of probability, a standing wave of existence smeared out over the entire shell. It wasn't anywhere in particular. It was, in a sense, everywhere in its orbital at once. This brings us to what is perhaps the single most famous and most profound experiment in all of science. It is the experiment that contains, as the great physicist Richard Feynman said, the heart of quantum mechanics. It is the double-slit experiment, but now performed with electrons. Let's walk through this together, very slowly. It is worth the time, because understanding it is to understand the core mystery of the quantum world. Imagine a wall. In it, we cut 2 very, very thin vertical slits, very close together. Behind this wall, we place a detector screen, like a photographic plate, that will show a little dot wherever something hits it. First, as a control, let's close one of the slits, say the right one, and keep only the left one open. Now, we get a special electron gun that can fire single electrons, one at a time. Pop! An electron flies out, goes through the open left slit, and makes a dot on the screen behind it. Pop! Another one. Pop! Another one. We do this for a long time. What do we get on the screen? A single fuzzy band of dots, clustered right behind the open left slit. This is exactly what you'd expect. It's like firing paintballs through a hole. They pile up behind the hole. Now we do the same thing, but we close the left slit and open the right one. As you can guess, we get a similar fuzzy band of dots, but this time it's clustered behind the right slit. Perfectly sensible. Now for the mystery. What happens if we open both slits at the same time. Classical intuition tells us what should happen. Each electron is a tiny particle. It must go through one slit or the other. It can't split in half. So over time, we should just get the two patterns we saw before added together. We should see two fuzzy bands, one behind each slit. But that is not what happens. When we fire the electrons one by one, with both slits open, something magical and inexplicable occurs. The dots on the screen do not form two bands. Instead, they build up one dot at a time to form a classic interference pattern, a series of many bright and dark stripes, just like the one Thomas Young saw with light waves. Think about what this means. The interference pattern is the hallmark of waves passing through both slits at once and interfering with each other. But we are firing electrons one at a time. The electron leaves the gun, and by the time it reaches the screen, the next electron hasn't even been fired yet. So the electron cannot be interfering with other electrons. It can only be interfering with itself. This implies that the single electron, in its journey from the gun to the screen, does not go through the left slit, nor does it go through the right slit. It goes through both slits simultaneously. As a wave of probability, it explores all possible paths. The wave passes through both slits, interferes with itself, and this interference pattern then guides where the particle is most likely to land on the screen. It's most likely to land where the wave constructively interferes, the bright stripes, and has zero probability of landing where the wave destructively interferes, the dark stripes. Let this idea breathe. A single particle, a fundamental constituent of your body, can be in two places at once. It travels as a wave of pure potential, and only when it hits the detector screen does it decide on a single location to be a particle. Before that moment of measurement, it is not a thing in a place. It is a possibility spread out in space. This state of existing in multiple states at once is called superposition. Naturally, the physicists who saw this were baffled. They thought, this is impossible. Let's try to trick it. Let's find out which slit the electron really goes through. So they set up a clever little detector right by the slits. A tiny beam of light, for example, that will register if an electron passes through the left slit or the right slit. Now we can watch. We have our spy. We turn on the machine. We fire the first electron. Our detector flashes. It went through the left slit, and we see a dot on the screen behind the left slit. We fire another. The detector says, right slit, and the dot appears behind the right slit. We keep doing this for thousands and thousands of electrons. We watch them go through the left, the right, the left, the left, the right. And what pattern do we get on the screen? The interference pattern is gone. It has completely vanished. All we see now are two fuzzy bands, exactly what we would expect for classical particles. The very act of observing which path the electron took forced it to choose a path. The moment we looked, the wave of possibilities collapsed, and the electron behaved like a well-behaved little marble. When we weren't looking, it acted like a mysterious wave, going through both paths at once. When we looked, it acted like a particle, picking one path. This is the observer effect. The universe, at its most fundamental level, seems to know when it is being watched. The nature of reality shifts depending on whether we measure it. This led to one of the most famous and profound principles in all of science, formulated by the German physicist Werner Heisenberg. It is the uncertainty principle. Heisenberg realized that this observer effect was not just a limitation of our instruments. It was a fundamental property of the universe itself. His principle states that there are certain pairs of properties of a particle that you can never know with perfect accuracy at the same time. The most famous pair is position and momentum, which is its mass times its velocity. The more precisely you know the position of a particle, the less precisely you can know its momentum. And the more precisely you know its momentum, the less precisely you can know its position. Imagine trying to find the exact location of a single tiny dust mote floating in a sunbeam. To see it, you have to bounce a photon of light off it and into your eye. But the dust mote is so small and light that the very act of hitting it with a photon will knock it off course, changing its momentum. If you use a very high-energy photon with a short wavelength to get a really precise measurement of its position, you give it a huge kick, making its momentum completely uncertain. If you use a very low-energy photon with a long wavelength, so you barely disturb its momentum, its long wavelength means you can only get a very fuzzy idea of its position. You can never win. The universe has a built-in trade-off, a fundamental fuzziness. The old classical dream of knowing the exact position and velocity of every particle in the universe, and therefore predicting the future, was dead. The universe is not a clock. It is a game of probabilities. These ideas formed the basis of what became known as the Copenhagen interpretation of quantum mechanics, largely developed by Bohr and Heisenberg. It says that particles exist in a superposition of all possible states until they are measured. The act of measurement forces the system to collapse into one single definite state. Erwin Schrödinger, another one of the architects of this new physics, was deeply troubled by this interpretation. He couldn't accept the idea of this collapse caused by an observer. To show how absurd he thought it was when applied to the macroscopic world we live in, he devised a famous thought experiment. This is the story of Schrödinger's cat. Let's be very clear. This was never a real experiment. No cats were ever harmed. It was a story designed to make a philosophical point. Imagine you have a box. Inside the box, you place a cat. You also place a tiny piece of a radioactive element. The atom is governed by quantum mechanics. Let's say it has a 50% chance of decaying in the next hour, and a 50% chance of not decaying. If the atom decays, it triggers a Geiger counter. The Geiger counter is hooked up to a hammer. The hammer is poised to smash a vial of poison. If the poison is released, the cat will, sadly, perish. Now, you close the box and wait 1 hour. According to the Copenhagen interpretation, the radioactive atom inside the box is in a superposition of states. It has both decayed and not decayed. Therefore, the Geiger counter is in a superposition of having been triggered and not triggered. The hammer is in a superposition of having fallen and not fallen. The poison is in a superposition of being released and not released. And therefore, the cat is in a superposition of being both alive and dead at the same time. It is only when you, the observer, open the box to check on the cat that the wave function of the entire system collapses into one of the two states. You will find either a live cat or a dead cat. But before you look, the theory says the cat is in an indeterminate, ghostly state of being both. Schrödinger thought this was ridiculous. A cat is either alive or it is dead. It can't be both. He intended this to be a criticism of the Copenhagen interpretation. But over time, the story has become the most famous illustration of the sheer strangeness of superposition and the measurement problem. Where is the line between the quantum world of atoms and the classical world of cats? How does a measurement happen? Does it require a conscious observer? These are questions that physicists and philosophers still debate to this day. It's interesting to note that even within this circle of revolutionary thinkers, there were critical voices from different backgrounds. A German philosopher and mathematician named Grete Hermann, for example, wrote an early critique of the Copenhagen interpretation. She argued that the uncertainty principle didn't mean that causality was dead, as some claimed. Instead, it meant that our classical concepts of position and momentum simply didn't apply perfectly to the quantum realm. She was pointing out that perhaps the problem wasn't that reality was illogical, but that our language and our classical ideas were not sufficient to describe it. Her work was largely overlooked for decades, but is now seen as an important early philosophical contribution to understanding these new physics. The story gets stranger still. Einstein, who had started the whole revolution with his idea of the photon, became its greatest critic. He could accept probability, but he could not accept some of the deeper weirdness. He famously said, "God does not play dice with the universe." He believed that quantum mechanics was incomplete. There had to be some hidden variables, some deeper reality we just couldn't see yet. That was determining the outcomes. The probabilities, he thought, just reflected our ignorance of these hidden variables. His deepest objection was to a phenomenon that he mockingly called spukhaft Fernwirkung, which translates to spooky action at a distance. This phenomenon is now known as quantum entanglement. Let's try to understand this gently. Imagine you create a pair of particles, say 2 electrons, in a special way so that their properties are linked. For example, particles have a quantum property called spin. For our purposes, we can just imagine it's like a tiny spinning top that can either be spin up or spin down. Let's say we create our entangled pair of electrons so that we know their total spin is 0. This means if one is spin up, the other one must be spin down and vice versa. They are intrinsically linked. They are part of the single unified quantum state. Now, we separate these 2 electrons. We send one to the other side of the room. We send the other one to the moon. They are millions of miles apart. According to quantum mechanics, until they are measured, neither electron has a definite spin. Each one is in a superposition of being both spin up and spin down. Now, an observer on Earth decides to measure the spin of her electron. The moment she measures it, its wave function collapses, and she gets a definite answer. Let's say she finds that her electron is spin up. Here's the spooky part. The very instant she measures her electron to be spin up, the electron on the moon, millions of miles away, immediately collapses its wave function into the opposite state. It becomes spin down. An observer on the moon measuring the spin at the exact same instant will find it to be spin down with 100% certainty. The information that the first particle was measured as spin up seems to travel to the second particle instantly, faster than the speed of light. This is what Einstein found so spooky. It seemed to violate his own theory of relativity, which states that nothing, not even information, can travel faster than light. Let's use a simple analogy. Imagine you have a pair of magic gloves. One is a left glove, one is a right glove. You put them into 2 identical sealed boxes without looking. You keep one box and you mail the other one to a friend in another country. While the boxes are sealed and traveling, you are in a state of uncertainty. The box you hold contains either a left glove or a right glove. You could say it's in a superposition of both possibilities. The moment you open your box and see a left-handed glove, you know, with absolute certainty, and in that very instant, that your friend's box contains the right-handed glove. This doesn't seem so spooky. No information traveled faster than light. The outcome was predetermined from the start. You just didn't know it. This is what Einstein believed was happening with entangled particles. He thought there were hidden variables, like the leftness or rightness of the glove, that were decided at the moment of creation. For decades, this was a philosophical debate. Bohr argued that there were no hidden variables, that the particles truly had no definite state until measured. Einstein argued that there must be. Then, in the 1960s, an Irish physicist named John Bell came up with a brilliant mathematical theorem. Bell's theorem provided a way to actually test this. It showed that if there were hidden variables, as Einstein believed, then the correlations between measurements on entangled particles would have to obey a certain statistical limit. However, if quantum mechanics as it stood was correct, the correlations would be stronger, violating that limit. It turned a philosophical debate into a testable experiment. In the 1970s and 80s, physicists like Elang Aspect and his team performed a series of incredibly precise experiments to test Bell's theorem. They created pairs of entangled photons and measured their properties at a distance. And the results were decisive. Einstein was wrong. Bohr was right. The universe is just that spooky. The experiments showed that the correlations between the particles were stronger than any hidden variable theory could allow. There is no pre-existing glove in the box. The two particles, no matter how far apart, remain a single interconnected system. Measuring one instantly affects the other. It's not that information travels faster than light. It's that in a way that defies our everyday intuition, the two particles are not separate things. They are two parts of a single non-local reality. This deep interconnectedness is one of the most profound insights of quantum physics. It tells us that the universe is not just a collection of separate objects. At a fundamental level, it is a web of relationships. It's also important here to acknowledge the monumental contributions of experimentalists who brought these theoretical ideas into reality. People like Chen-Xiang Wu, a Chinese-American physicist often called the First Lady of Physics. In a famous experiment in 1956, now known as the Wu experiment, she and her team conducted a meticulous and difficult experiment that overthrew a long-held law of physics called the conservation of parity. This law stated that the universe should be indifferent to mirror images, that the laws of physics should be the same for a process and its reflection. Wu's experiment, which involved cooling radioactive cobalt atoms to near absolute zero, proved that this was not true for the weak nuclear force, one of the four fundamental forces of nature. Her work was a cornerstone of particle physics, and a testament to the power of precise, careful experimentation in revealing the universe's true nature. She, like so many others, built the solid experimental ground on which these strange quantum theories stand. Now you might be thinking, as you drift deeper and deeper into a state of relaxation, that this is all very fascinating, but very abstract. What does this strange world of superposition, entanglement, and uncertainty have to do with my life? With the solid, predictable world around me? The surprising answer is everything. Without quantum mechanics, the modern world would not exist. The technological revolution of the 20th and 21st centuries is built from the ground up on our understanding of the quantum realm. Let's start with the device you might be listening to this on. A smartphone, a computer, a tablet. The heart of these devices is the microchip, and the microchip is made of billions of tiny switches called transistors. A transistor works by controlling the flow of electrons through a special material called a semiconductor. To design and build a transistor, engineers must have a deep understanding of the quantum behavior of electrons in materials, their wave functions, their energy levels, their probabilities. The entire digital age is a direct consequence of our ability to manipulate the quantum world. Consider the laser. The word laser is an acronym for light amplification by stimulated emission of radiation. The key word there is stimulated emission, an idea first proposed by Einstein. It's a purely quantum process. In a laser, you pump energy into a material to get a lot of its electrons into a higher energy state, a higher rung on Bohr's ladder. Then, a single photon of the right energy comes along and stimulates one of the electrons to drop down, releasing an identical photon. This new photon is perfectly in sync with the first one. The same color, the same direction, the same phase. Now you have two photons, which can go on to stimulate more electrons, creating 4 photons, then 8, and so on. This creates a cascade, an avalanche of perfectly coherent, organized light. This is what makes laser light so focused and powerful. It's used in everything from barcode scanners at the grocery store to fiber optic communication that carries the internet to delicate eye surgery, all thanks to quantum leaps. What about medical technology? The MRI scanner, or magnetic resonance imaging, is a powerful diagnostic tool that allows doctors to see soft tissues inside the body without surgery. It works by using the quantum property of spin. The nuclei of the hydrogen atoms in your body's water molecules act like tiny spinning magnets. The MRI machine uses a powerful magnetic field and radio waves to align these spins and then knock them out of alignment. As the spins relax back into alignment, they emit a faint signal that the machine can detect. By analyzing these signals, a computer can build a detailed 3D map of your body's organs and tissues. It's a direct application of manipulating a purely quantum property. Even the GPS in your car or phone relies on quantum mechanics. The GPS system works by triangulating your position from signals sent by at least 4 satellites orbiting the Earth. For this to work, the timing has to be incredibly precise. Each of these satellites carries an atomic clock, the most accurate timekeeping devices ever created. And an atomic clock works by tuning an oscillator to the precise, unvarying frequency of photons emitted by electrons jumping between 2 energy levels in an atom, like cesium. It's the consistency of Bohr's quantum leaps that provides the perfect, reliable tick for these clocks. So the next time you use your phone, watch a Blu-ray disc, or see a laser light show, you can let a quiet thought of thanks drift to those early quantum pioneers. Their struggle to understand a strange glow from a hot object or the behavior of an electron in an atom laid the foundation for the world we live in today. And the quantum revolution is far from over. We are now on the cusp of a second quantum revolution, one that seeks to not just use the side effects of quantum mechanics, but to harness its most bizarre features, superposition and entanglement, directly. This is the field of quantum computing. Let's think about a classical computer bit. It's like a simple light switch. It can either be off, which we represent as a 0, or it can be on, which we represent as a 1. All the complex things your computer does are built up from billions of these simple binary choices. A quantum computer, on the other hand, uses qubits. A qubit is not a simple switch. It's more like a dimmer switch. But it's even stranger than that. Because of superposition, a qubit can be a 0 or a 1, or, and this is the key, it can be both 0 and 1 at the same time. Think of it this way. A classical bit is a coin lying on a table. It's either heads or tails. A qubit is like a spinning coin. While it's spinning, it's not heads or tails. It's a blend of both possibilities. Only when you stop it, by measuring it, does it land on one definite state. Because a qubit can exist in a superposition of states, a quantum computer with just a few qubits can explore a huge number of possibilities all at once. 2 qubits can represent 4 states simultaneously: 0, 01, 10, and 11. 3 qubits can represent 8 states. With just 300 qubits, a quantum computer could represent more states than there are atoms in the known universe. This gives quantum computers the potential to solve certain types of problems that are practically impossible for even the most powerful classical supercomputers. Problems like designing new medicines by simulating molecules with perfect quantum accuracy, or creating new materials with desired properties, or breaking complex cryptographic codes. Furthermore, by using the spooky action of entanglement to link qubits together, a quantum computer can perform calculations where the state of one qubit is instantly correlated with another, allowing for incredibly complex and powerful algorithms. Building and controlling these machines is an immense scientific and engineering challenge. Qubits are incredibly delicate. The slightest disturbance from the outside world, a stray vibration, a change in temperature, can destroy their fragile superposition, a process called decoherence. It's like trying to get a coin to stay spinning on its edge. The slightest breeze will make it fall. This is why quantum computers today are large, complex machines, often kept at temperatures colder than deep space, shielded from the rest of the world. We are still in the very early days of quantum computing. It's like the 1940s for classical computers, the era of room-sized machines with vacuum tubes. But the promise is immense. It's a new way of harnessing reality, of computing with the universe's own strange and wonderful operating system. And what other secrets is the quantum world waiting to reveal? There are still so many mysteries. One phenomenon, which is crucial for the very existence of our sun, is called quantum tunneling. According to classical physics, if you roll a ball towards a hill, it needs enough energy to get over the top. If it doesn't have enough energy, it will simply roll back down. It can never get to the other side. There is a barrier it cannot cross. But in the quantum world, things are different. Because particles are also waves of probability, their wave function doesn't just stop at the barrier. It decays, but a tiny part of the wave can actually leak through the barrier. This means there is a small, but non-zero, probability that the particle will simply appear on the other side of the hill, even though it didn't have enough energy to climb it. It has tunneled through the barrier. It's like a ghost walking through a wall. It shouldn't be possible, but the laws of quantum probability allow it. This very process is what allows the sun to shine. The core of the sun is hot, but it's not quite hot enough for hydrogen nuclei to overcome their mutual electrical repulsion and fuse together in the classical sense. But because of quantum tunneling, they have a chance to get close enough to each other to fuse, releasing the immense energy that powers our solar system and makes life on Earth possible. The warmth you feel from the sun on your skin is a direct result of this ghostly quantum trick. And what about the big questions? We have these two majestic theories of physics. On one hand, we have Einstein's general theory of relativity, our best description of gravity and the universe on a large scale, the scale of planets, stars, and galaxies. It describes a smooth, curved spacetime. On the other hand, we have quantum mechanics, our best description of the universe on the smallest scales, the scale of atoms and particles. It describes a jittery, probabilistic world of discrete quanta. The two theories are both incredibly successful in their own domains, but they don't play well together. They speak different languages. When you try to use them together, for instance, to describe what happens at the center of a black hole or at the moment of the Big Bang, situations where you have immense gravity in a tiny space, the equations break down and give nonsensical, infinite answers. The search for a single, unified theory that can gracefully describe both the very big and the very small is the holy grail of modern physics. A theory of everything. There are several promising candidates, like string theory, which proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings of energy, with different vibrations corresponding to different particles. Another is loop quantum gravity, which suggests that space-time itself is not smooth, but is made of tiny, discrete quantum chunks. These ideas are still highly speculative and mathematical. They are on the furthest frontiers of human knowledge, but they represent our unending quest to find a single, elegant description of the universe. And what of the interpretation of it all? The Copenhagen interpretation, with its collapsing wave functions, is still the most commonly taught version, but it is not the only one. There are other ways to think about the mystery of the double-slit experiment. One of the most mind-bending alternatives was proposed by a young physicist named Hugh Everett III in the 1950s. He, like Schrödinger, was bothered by the special role of the observer and the collapse of the wave function. He asked, what if the wave function never collapses? Everett proposed that when a quantum measurement is made, the entire universe splits. When the electron faces the two slits, the universe divides into two. In one universe, the electron goes through the left slit. In another, parallel universe, a copy of you sees the electron go through the right slit. Every quantum event, every possibility, plays out in its own separate reality. This is the many worlds interpretation. In this view, the cat in Schrödinger's box is never in a superposition. The universe simply splits into one branch, where the cat is alive, and another where it is dead. There is a version of you who opens the box and finds a happy, living cat, and another version of you in a separate universe who opens the box and finds a tragic outcome. There is no way to test this idea, as we are trapped within our own branch of reality. But for some physicists, it is a more elegant and complete solution. It removes the strange measurement problem and treats the entire universe as one giant evolving quantum system. It is a vast, almost terrifyingly grand vision of a branching, ever-multiplying cosmos, with infinite versions of reality playing out all the possible outcomes of every quantum choice. Let's just rest with that thought for a moment. Not as a truth, but as a possibility. A gentle, branching river of realities, flowing from the past into the future. It's a concept that stretches the mind, and that's a good thing. It reminds us that the universe is not only stranger than we imagine, it is stranger than we can imagine. So as we bring our long, winding journey to a close, let's drift back from these grand cosmic ideas to the quiet space where you are now. to the gentle rhythm of your own breath. What can we take away from this journey into the quantum realm? It is not about memorizing facts or understanding equations. It is about a shift in perspective, a quiet invitation to see the world with a little more wonder. Quantum physics teaches us that the world is not made of solid, separate, machine-like parts. It is a world of shimmering potential, of interconnectedness, of deep and subtle relationships. It teaches us that uncertainty is not a flaw, but a fundamental feature of reality. There is a built-in fuzziness, a gentle give and take at the heart of existence. We cannot know everything with perfect certainty, and perhaps that is a beautiful thing. It leaves room for surprise, for novelty, for the universe to be creative. It teaches us that connection can be deeper than we ever imagined. The idea of entanglement, of two particles linked across vast distances, hints at a universe that is not a collection of lonely objects, but a single holistic entity. It suggests that separation may be, in some profound sense, an illusion. And it teaches us that we are not merely passive observers of the universe. We are participants. The act of observation, of measurement, of asking a question, changes the answer we receive. We are in a delicate dance with reality. We are part of the system we are trying to understand. So as you lie here, ready to drift into sleep, feel the gentle hum of this quantum world. It is not something far away in a laboratory. It is here. It is now. It is in the sunlight that warmed the planet today. It is in the silicon chips that carry these words to you. It is in the very atoms that make up your body. The electrons in your own cells exist as clouds of probability. The chemical bonds that hold you together are a quantum dance of shared electrons. Let yourself feel a sense of peace with the strangeness. The universe doesn't have to make sense in the way a clock makes sense. It can make sense in the way a poem makes sense, or a piece of music. It can be mysterious and paradoxical and breathtakingly beautiful all at once. The world is not a static, solid thing. It is a dynamic, effervescent, and endlessly creative process. A constant shimmering between being and becoming. A quiet dance of probability and potential. And you are a part of that dance. So just let go. Let these ideas wash over you like gentle waves on a cosmic shore. There is nothing to solve, nothing to figure out. Just a deep and peaceful wonder at the incredible, intricate, and mysterious universe we are so lucky to be a part of. Take a deep, slow breath, and as you exhale, let go of all the thoughts of the day. Let the shimmering quantum mist surround you, and drift. Drift peacefully. Drift deeply. Sleep well.